less than 24 hours, the moon's shadow will sweep across Earth during the total eclipse of August 12, 2026. But instead of just showing you where the eclipse is happening, I pulled NASA's actual eclipse-path data into Python, and I found something I didn't expect. The widest part of the eclipse path is not where totality lasts the longest. So let's look at the data. Hello, I'm Dr. Amanda Fetch, aka Dr. Amanda Analytics, and welcome back to Take AI Space Oh My, where we dig into the data and the technology behind what's happening in space. Now, tomorrow's path of totality crosses the Arctic, Greenland, Iceland, the Atlantic, and parts of Spain and Portugal. But I wanted to go beyond the map and see what NASA's actual eclipse predictions tell us. Now, NASA publishes detailed path data for the eclipse, including the northern and southern limits of totality, the central line, the sun's altitude and azimuth, the width of the path, and how long totality lasts. Now, I pulled NASA's path table, which gives us observations every 2 minutes, from 1702 through 1832 Universal Time. I did a little cleaning in Excel first. The raw coordinates contain spaces, so I imported the data using fixed width columns to keep the latitude and longitude values together. I renamed the columns, removed the blank separator rows, and then brought the data into Python. Now I used pandas to work with the data and Matplotlib to visualize it. That's really where all the pre-processing takes place, and really I'd say the extent of what we need to refer back to. Now, because the charts are really where this gets interesting. Now first I plotted how long totality lasts as the eclipse progresses. Now look at the curve. Totality starts at about 106 seconds in the first sample point, climbs to a maximum of about 138.2 seconds, or 2 minutes and 18.2 seconds, around 1744 UT, and then begins falling again. By 1832, it's down to about 96 seconds. Now NASA's more precise calculation places greatest duration at 1744.42 UT. So our analysis lines up with NASA's published result. Then I plotted the width of the path of totality, and this is where I noticed something interesting. At the point where totality lasts the longest, the path is about 292 kilometers wide. But the path keeps getting wider after that. Now between roughly 1814 and 1820 UT, reaches about 319 kilometers wide. And by then, totality is already getting shorter. At 1814, it's about 127 seconds, and by 1820, it's about 121 seconds. So the path is getting wider, while totality is getting shorter. That's what I find interesting. Now, you might assume that a wider path means a longer period of totality. But these two charts show why that's not necessarily the case. The longest totality occurs around 1744 UT, while the widest portion of the path occurs roughly half an hour later. Now, I compared width and duration across the dataset, and the simple correlation was only about 0.14. Very weak positive relationship in these observations. Now, that doesn't mean width and duration aren't related in eclipse physics. It means width alone doesn't explain how long totality lasts along this particular eclipse path. And the reason comes down to geometry. The moon's shadow is intersecting at a curve, rotating Earth while the shadow itself moves across the surface. The orientation of that shadow changes as the eclipse progresses, so the width of its footprint on Earth and the amount of time someone spends inside that shadow doesn't necessarily reach a maximum at that same moment. Now, that's part of what makes eclipse predictions such an interesting mathematical problem. So, if you're watching tomorrow, remember that only people inside the path of totality will see the sun become completely covered. Now, even within that path, what you experience depends on exactly where you are at. At the maximum, we're talking about maybe just over 2 minutes of totality, an astronomical event calculated years in advance, stretching across thousands of kilometers, with its most dramatic moment lasting only a couple of minutes. So I also wanted to leave an important reminder. Now, during the partial phases, make sure you wear proper solar viewing protection. Ordinary sunglasses aren't going to cut it. Only during complete totality, when the bright face of the sun is entirely covered, can observers within that path of totality briefly view it without solar filters. Now, as soon as that sun begins to reappear, the protection goes back on. Now, with that being said, this is why I love digging into publicly available data. We started initially with this video looking at NASA's eclipse predictions. We pulled that data into Python, And when we looked at those visualizations, they showed us something that isn't immediately obvious from looking just at a simple eclipse map. The widest part of tomorrow's eclipse path isn't where totality lasts the longest. Now, if you check out the description, I went ahead and I put the NASA data source in that description. And if you want to explore it yourself, now you have the opportunity to do so. And with that being said, I want to leave you with a question. Will you be watching the eclipse tomorrow? And where will you be watching from if so? Let me know in the comments. This is Dr. Amanda signing off, saying keep looking up and keep asking questions. Thanks for tuning in. Take care.